Okay, so here is our numerical integration handout. There are two sides to it, and we're going to use Excel to solve the problem. So you can see the integral I chose, or the equation I chose, is fairly well. We couldn't solve it using analytical techniques, using what we know so far. And what we want to do is we want to start at some initial condition, which is x equals 0, y equals 2. And we want to find the solution from 0 to 2 using a step size of 0.1. Plot the solution y versus x, do all this using Excel, write the x, y values, the solution of the values shown in the table. So this is just a way of summarizing that we've done it correctly. So I'm going to write this equation down on a piece of paper so that I can, so you might want to do the same thing so we don't have to keep looking back. So we're going from x equals 2 to from 0 to 2. Okay, so let's move to Excel. So here's Excel. So the first thing you need is a column that we're going to call n, which is just the step, starting with step number 1. And then we're going to have a column which is x, that's the x value. And then we're going to have f prime of x. And then we'll have, what are we going to have? We need the function f of x. And we need, I guess that's it. We'll see how it goes. So we're going to start, actually we're going to start with n equals 0. So in Excel you can put in numbers, and we're going to increment. And because we have a step size of 100, and we're going from 0 to 2, that means we need 200 steps. So you take 2 divided by 0.01. Okay, so we need numbers from 0 to 200. So I'm just going to, what you do is you highlight the two cells that you've manually entered. Then you grab the corner, a little square in the corner, and you drag it down. We're going to drag it down until we get to 200 and something. Just a little past 200. We can always delete stuff when we get there. Okay, so we're just going to highlight those cells, push delete. So we have steps, 200 steps. Our initial condition is x equals 0 and f of x equals, what was it equal to? Where's my handout? Y equals 2. Okay, so that's y equals 2. So let's go to, let's make up a fresh sheet of paper here. So the way it works is we say that f, the function at some new step, n plus 1, equals the function at the previous step plus the derivative of the function evaluated at n times delta x. So this is going to give me this part's going to give me a delta change in the function value. So this is kind of like slope, and I'm multiplying by delta x. That'll give me delta y. So we know the value of the function derivative. Y prime is equal to x squared sine of x squared plus 3. So we can evaluate, when we say f prime of n, we're going to evaluate the function at the current value of n, say x sub n squared sine of x sub n quantity squared plus 3. So we're going to evaluate the derivative, and then we can say that the new value of the function is the old value of the function plus what we just calculated. So we'll have this in a separate cell, and then we'll multiply that by delta x, which is 0.01. That's our increment. Okay, so let's do that. So we're going to evaluate the derivative, and the derivative is equal to x squared. So we'll click on the cell for x, and we'll square it. If I can square it, there we go, x squared times the sine of x, cell B2 squared, close parentheses, plus 3. So that's the derivative value of the derivative. So what we'll start off is 0 squared plus the sine of 0 squared plus 3. So it should be 3. Okay, so that's f prime of x. Now, our new value of the function is going to be equal to, go back here, it's going to be equal to the old value of the function plus the derivative times 0.01. So we're going to take the old value of the function plus the derivative at the previous step times 0.01. So that's my new value of the function. And my new value of x is 0.01 because we're incrementing x by 0.01. So let's go ahead and fill out the this entire column. So we're going to highlight the first two cells, and then we're going to drag the corner all the way down to the end, and it should come out to around 2, if I did this right. 2, yeah. Okay, so there, that's our x values. Now we're going to do the same thing here, and the equation that we had before should still work. And if I copy this down, I think you copy by clicking on the cell, going to this little square in the corner and dragging it in. That'll give me the updated value for the derivative, and something seems wrong because it seems awful small. Let's just do it a few more times. Yeah, okay, so it's just because it was so small, so let's just delete that. So it actually did change. So it's going to take, it says B3 squared, so you take this squared times the sine of this quantity squared, and then you add 3 to it. Okay, so, and then the function is going to be updated as well, so that equation applies, and it's going to use the most, it's going to increment the cell, so everything should be working. So we'll just take that and we'll highlight these two cells, and then we'll drag it all the way down to the bottom so we get to 200, and there you go. Okay, so this is the x value, this is the y value, and you can see that first function increases. It actually does keep increasing, but at some point, and it's because the fact that the sine of x is going to go from 0 to 1 to 0 back to -1, so this thing is not going to just continually increase. Okay, so that's how it works. So you take you evaluate your derivative at first step. You multiply that derivative times the time step, or the x change, which is 0.01, add it to the previous value. That gives you your delta y, so you keep updating y as you go along. Now, to plot this thing, you go to Insert, Charts, and you'll see this one with little dots. That's a scatter plot. Now this is going to automatically pick things that I don't really want, so I'm gonna pick it, but then I'm gonna make some changes. So to edit the graph, it's good to move it out from the data. So you go up to here to where it says Move Chart, and click New Sheet, and say OK. Okay, so there's my graph. And let's go back to the original sheet. So if you go down to the corner here, it says Sheet 1. What I want to do is I want to plot y versus x. I want to plot this column versus this column. So the best thing to do is to go back to your chart and pick Select Data, and just remove all the stuff that you have on here. So we got all it removed. We'll start from the beginning. So first thing to do is we're going to add the the data. So it says series name. Well, we only have one series, so we don't need to put a series name. X values. So we click on that, and then we go back to our data, and we're going to highlight all the X values from 0 to 2. So this is the X values, and you press enter. And then you pick the Y values. So the Y values are in column D. You highlight all those. So you get to the bottom, push enter, say OK, and OK. So that is the solution to the differential equation. So for a given X, there's one value of Y. You see how it increases pretty linearly until you get to about here, and then it starts to level off. And we could make some changes. If you click on different parts of the graph, you can change the title here. So if it's the title, sometimes if you double click in there, and I'm just trying to change the title name. So let's just, it didn't like that. Okay, let's try something else here. Format. A lot of times if you right click, let's see if that works or not. Yeah, okay. This is a different version of Excel than I'm really used to, so it takes me a while to remember how to do things. Let's just get out there for a second. Okay, I'm going to pause for a second because I got to figure this out. Okay, so what you do is you click on the graph, and you'll see this little plus sign on the right. So I want axis titles, and then you can click on them, and let's see if there's more options here. I think you got to click in the title area, so we'll go down here to the x-axis, and we'll click in there, and now we should be able to put it. So this is X variable, and if we go to home and font, we should be able to increase the font. So I think you've got to highlight. Got to highlight what you want to do, so we can change that to a bigger thing. Okay, so there's your X variable. Then you go over to the Y-axis title, and I think you can make some modifications in there. So that would be Y variable. I need to highlight all those things inside. So we need to make it bigger. So there's the Y variable. Again, if you go here, you can put chart titles up there, so now you can see the chart title. And we could say solution to equation. And you can make the numbers bigger. So if you click on the numbers down here and then right click, oh, you can see here, well, if you right click it and choose font and then increase the font size to 14 again. So that makes those bigger, and you go over to the Y-axis and you can change those. I think if you go to home, you can change them there. It looks like those are already changed. Yeah, they must both got changed when I did that. Okay, so that helps. Got bigger numbers. So anyway, that's the solution. So to fill in the chart that we have, which is somewhere here. Yep. So what you do is just go to these different values of X in the data. So the first one is X equals 0.5. So let's just scroll down. So X 0.5 is Y equals 3.5059. That one right there. Put that in your paper, and you can scroll down to X equals 1, which is right here. So Y is 5.1779. Then you could do 1.3. That's right here. 6.456. And 1.7 is right here. 8.286. Okay, so that's how you would numerically integrate an equation. And you don't end up with an equation, you end up with a graph. Okay, the next example on the back, it says find the area underneath the curve. So this is kind of similar. So if you're given the function, not the derivative, you're given f of x and not f prime of x. And what it says is it wants to find it between x equals 1 and x equals 5. And again, this is, if we wanted to find the area, we would integrate f of x dx from 1 to 5. Now what we're going to do is use the trapezoid rule here, which means that we're going to be able to define a trapezoid. The height of the trapezoid is going to be 0.01. You can see that in the description. Let's just look at that. So if you go to the next page, so it says the width of each trapezoid is 0.1, and we should have 400 trapezoids because we've got 100 for 1 to 2 and 100 from 2 to 3 and so forth and so on. So you should have 400 trapezoids, and we'll add those areas together. So what we're going to do is we're going to do a new spreadsheet here. And what we need to do is we need a column with n again. We need x, we need f of x. And then we're going to calculate the area for each trapezoid. So let's start at 0, go to 1, and we have to have 400 of these. So let's highlight this 2, drag it down to 400 and something, a little after 400, just so if I count wrong, it's always easier to delete stuff than it is to, so I'm just going to delete those, highlight them, delete them. So we got 400, and our x value starts at the value of the, well, x starts at 1, and then we increment. So one way to increment this is, because we're starting at 1 and not at 0, is we would say it's the equals, put the equal sign in there, the old value of x plus 0.01. So you get 1.01, and then we could just take that formula and drag it down all the way down until we get to the end. And it should be 4 when it gets to the end, 5. Okay, so you can see it goes between 1 and 5. Okay, then we need to calculate the value of the function. So the function is equal to x, which is this value, squared minus 1, and then raise that whole thing to the 3/2 power. Okay, so you can see the value of the function at x equals 1 is 0. And that makes sense because, you know, you're going to have 1 squared minus 1, which is 0. 0 to 3/2. Okay. Now, let's just copy this one time down. So the area for the second, or the value of the function at x equals 1.01 is this. Now the area of a trapezoid is you take the width, which is 0.01 in this case, and you multiply by the average of these two. These are the heights. So we're going to take this plus that and then divide by 2. So it's the height of the trapezoid, which is 0.01, and the average of the bases. So for this first area, first case, we get an area of a very small number. So now that we've got the equations written, and they're going to be updated as we copy these down, we're going to highlight both of these together, grab the corner, drag it all the way down to the bottom again, and we'll get all that. So these are the values of the function. These are the areas for each value, and we say equals sum. That means we're going to add all these areas up, and then so you highlight the area that you want to add up, and you get 138.64. So that's the answer, 138.64. Now let's go to a definite integral calculator on the internet. So definite integral calculator. So this is something we've shown before, and we'll put the equation in and we'll see how well it matches up in terms of the results. So we're going to do the integration. We're going to integrate from 1 to 5, and our function is x squared minus 1, and then the whole thing raised to the 3/2 power, like that, and we say go. And it's just thinking and thinking and thinking. Steps are currently not supported for this problem, but I think it still gives us an answer. Well, you can definitely see why we'd have to do this by numerical integration. The question is, why it isn't giving me an answer? Okay, interesting. Another way we could plot this function and then just estimate whether this number makes sense or not. So let's do that instead. So it says 138.6. So we're going to get the grapher program here, and we're going to plot the function. So we're going to have x squared minus 1, whole thing raised to the 3/2 power, and we want to go from 1 to 5, and we're going to have to zoom out in the x direction. Okay, now the question is, what the heck is the area underneath this curve? So one thing you could kind of do is, if we drew a horizontal line here at what I calculate the average value to be based on this. So the average value would be the integral 138 divided by 4, which is the x change. So 138 divided by 4, 38 divided by 4 is 35 approximately. So if I draw a horizontal line at 35, you'll get that. So what it's saying is that this area here has to equal this area here. What I'm looking for is actually the area under the red curve. But if this is the correct average value for the whole calculation, the area above the curve here has to equal the area below the curve there, which it looks like it's a pretty good, looks pretty reasonable. So it seems like this is actually a pretty good answer. Okay, so that's it. So you can use both numerical integration to solve differential equations as well as find the area underneath the curve. I may see if I can, don't quit yet. I'm going to put myself on pause here for a moment. Okay, so there's this Wolfram Alpha widget, and you can see that I put in x squared minus 1 quantity to the 3/2 power from 1 to 5, and you can see it comes up with 138.643, which compares 138.644. So definitely the right answer. So let me explain what we did there. This was the value, this was f of x, and this would be f of x plus delta x. So when we were evaluating the area, so you can see this, if we go back up to the beginning, the area is delta x, which is this width, times the average of these two values. So I take the average, see this function here plus this function there, average of the two, that gives me the average of the bases, and that gives me the area. And then all I'm doing is I'm just stacking all these little trapezoids next to each other, and you see it came out pretty close to the final answer, just using it's called the trapezoid rule.